All right, you've probably heard of scalars and vectors. I mean, we all learned about them in school, right? Simple stuff like temperature or velocity. But there's this other thing, this more powerful object that shows up everywhere, from engineering all the way to Einstein's theory of relativity. It's called a tensor. And let's be honest, it's famous for being confusing. So today, that's what we're going to do. We're going to build an intuition for what a tensor really is, right from the ground up. And believe it or not, this whole deep dive, it all boils down to one simple but really powerful question. What if the direction of a cause didn't match the direction of its effect? I mean, what if you pushed something forward and it moved sideways? I know, it sounds totally bizarre, but that one weird idea, that's the key to everything. Because once you start trying to answer that question, it completely shatters our basic high school level understanding of physics. It doesn't work anymore. We're forced to find a whole new framework, a new language, really, to describe how reality works. And yep, you guessed it, that language is the language of tensors. So let's get right to it. What the heck is a tensor? You know, most of us have probably heard the word, but the definitions you find online or in textbooks, they're usually super vague or just not helpful at all. So we're going to do something different. We're just going to set all that aside and rediscover this idea for ourselves. Okay, let's start with what we already know. We've got scalars. A scalar is just a single number, right? Like the temperature in a room. It's just a value. Then you have vectors. A vector takes that number and adds a direction. Think about velocity. You're not just going 60 miles per hour, you're going 60 miles per hour north. Pretty straightforward. But then you ask about tensors, and you get something like this. It's kind of like a matrix, but think in terms of indices. And I mean, come on. That doesn't really build any intuition, does it? It's exactly why so many of us just walk away totally confused. We need a much, much better starting point. Okay, so to build this whole idea from scratch, we're going to start with something we all might remember from physics class, Ohm's law. We're going to look at a version where we have an electric field, that's a vector, and it causes a flow of current, which is another vector. Simple setup. Now, the thing that connects these two vectors is a property called conductivity. It's really just a measure of how well a material lets electricity flow through it. You know, a higher number means it's a better conductor. In our simple high school physics model, this is almost always just a single number. But this is where things start to get way more interesting once we dig a little deeper. And this right here, this is the central question of our whole journey today. So imagine you've got a block of some random material. How many numbers do you actually need to write down to completely, totally describe its conductive properties? Think about it. So, the most obvious first guess is 1, right? Just one number. If the conductivity is just a single value, let's say 3, it just means you get 3 units of current for every 1 unit of electric field you put in. Super simple. But this makes a huge assumption about the material itself. See, that one number idea only works if the material behaves the exact same way in every single direction. But what if it doesn't? Take a crystal like graphite. It's made of these layers, and electricity flows super easily along the layers, but it can barely get across them. Materials like this are called anisotropic, and they just completely break our simple one-number model. Okay, so if one number isn't going to cut it, what's our next logical guess? Well, we live in 3 dimensions, right? So maybe we just need 3 numbers. One for how well it conducts in the x direction, one for y, and one for z. That seems like it should cover all the bases, shouldn't it? But this is where things get really, really weird. Because even with 3 numbers, our model is still incomplete. We're about to see something that doesn't just tweak the model, it fundamentally challenges our whole idea of cause and effect. Think about almost every physics equation you've ever seen, like F equals ma. You push a box forward and it accelerates forward. The cause, the force, and the effect, the acceleration, are perfectly lined up. But in our weird crystal, something else happens. We apply an electric field in one direction, and the current actually flows off in a totally different direction. The cause and effect factors are misaligned. This is a huge deal. So that begs the question, why did our 3-number model even seem to work at all? Well, it turns out we just got lucky. We accidentally set up our experiment in a way that hid all the real complexity of what was going on. So what probably happened is we set up our experiment by perfectly aligning our measurements with the crystal's natural easy and hard directions of flow. And if you apply an electric field right along that easy x-axis, guess what? The current flows right along with it. Cause and effect line up, Everything looks simple, and we think our model is great. And this is the aha moment. You got lucky. We accidentally chose our axes to line up perfectly with the special directions inside the crystal. And in doing so, we made the whole problem seem way, way simpler than it really is. That weird non-alignment was completely hidden from us. So what happens if we're not so lucky? What if we rotate our whole coordinate system to some random arbitrary angle? Well, now things get interesting. An electric field that is purely in our new x direction suddenly produces a current that has components in both the new x and the new y directions. Bam! The hidden complexity is right there in our faces. A single cause is now creating effects in multiple directions at once. And this little table here shows us exactly why we need more numbers. Check it out. To figure out the total current flowing in the x direction, you need to know how the x part of the electric field affects it and how the y part of the electric field affects it. There's this crosstalk happening. The same thing is true for the y current. So in just 2 dimensions, we don't need 1 number, or even 2, we need 4. Okay, so let's bring this all back to our real 3D world. If we needed 4 numbers, that's 2 squared for 2 dimensions, how many do you think we need for 3 dimensions? You got it. We need 3 squared, 9. We need 9 separate numbers to fully, completely describe conductivity. And just like that, with that one discovery, we can finally see how this all fits together. We haven't just solved a weird crystal problem, we've stumbled upon a whole new way of classifying physical quantities. It's like finding out that our old friends, scalars and vectors, are actually part of a much bigger, much cooler family. Just take a look at the pattern here. It's so elegant. We can now go back and rename things. A scalar, that's just a rank 0 tensor. In any n-dimensional space, it needs n to the power of 0 components, which is always just 1. A vector, that's a rank 1 tensor. It needs n to the power of 1, or n, components. And our conductivity, this new beast, it's a rank 2 tensor, needing n squared components. See? It's all one beautiful logical family. And get this isn't just some weird niche thing about electricity. This same exact principle is hiding all over physics. You know, moment of inertia? That's a tensor, because when you spin something, its axis of rotation isn't always perfectly aligned with its angular momentum. Stress in a material, that's a tensor too, because when you push on a surface, the resulting force inside isn't always perfectly perpendicular to it. Basically, anytime cause and effect can get misaligned, you can bet a rank 2 tensor is lurking in the background. So you see, this is way more than just a clever math trick for figuring out weird crystals. This way of thinking, this whole framework, this is what allows us to describe the very fabric of reality itself. It is the language of modern physics. So after all of that, we can finally come up with a definition that actually feels intuitive. The best way to think about a tensor is as a kind of machine. It's a machine that you feed an input vector into, it does some complex transformation inside, and it spits out a new output vector. And here's the most important part. The physical reality that this machine describes is the same no matter how you look at it, no matter what coordinate system you use. Because after all, nature doesn't care one bit about our imaginary x, y, and z axes. And that leaves us with one final kind of mind-bending thought to chew on. We just learned that stress, the force that deforms a material, is a tensor. Okay. Well, Einstein's theory of general relativity tells us that mass and energy cause stress in the fabric of space-time itself. So what does it even mean that space-time itself can be stressed and warped, and that this warping is described by the exact same kind of mathematical object we needed for our simple little crystal? That question? Well, that takes us right to the heart of Einstein's universe.